Hi, this is a lecture on uniform circular motion, and the slides are from OpenStax Physics. So let's talk about Newton's laws of motion. Newton's laws of motion primarily relate to objects that are moving in a straight line, whether it's horizontal, vertical, or at an angle. However, we can also talk about objects that are moving in a circuit, in a circle. And in particular, we're going to talk about uniform circular motion, which is motion on a circular path with a constant speed. So, in order to think about the difference here, let's compare how it feels if you're a passenger in a car moving at a constant speed. If you're traveling in a straight line versus if you're going around a tight turn. I want you to pause the video and think about this for a minute. Okay, so if you've been a passenger in a car traveling in a straight line at a constant speed, it feels pretty comfortable as long as your car has a good suspension system and it's a smooth road. You feel pretty normal. It's almost like you're just sitting down in a chair that's not moving. However, if you go around a tight turn, you might notice that you feel like you're pushed outward towards the outside of the car or outside of the curb. And that's a hint that tells us about uniform circular motion. Since we feel like we're experiencing some sort of force there, that gives us a clue that uniform circular motion is not an equilibrium situation. There is actually going to be a force acting in that scenario. So let's look at another scenario. A yo-yo is spun around horizontally in a circle at a constant speed, and it's released at the top of the path here. Make a hypothesis about what will happen. Which path will an object most closely follow when the centripetal force is removed? That is, when you release the yo-yo. Pause for a second and think about this one. Okay, so when that yo-yo is released, it's at this point. And if we're thinking about the velocity of the yo-yo at this point, it's moving to the right. It's moving tangential to the circle. So, though you might expect it to move in this A path, that's not actually what happens. When we remove all forces from an object, it'll just travel in a constant velocity. So it's going to travel in a straight line, and it's going to follow the path of B, just by Newton's law of inertia. It does, if you continue rotating, it might look like it's getting farther away from you, but that's because it is getting farther away from you as it travels along this line. But it'll travel in a straight line once that force is removed, a tension force. So let's look at some uniform circular motion to figure out some equations. Here we have an object that's rotating about in a circle, and it's traveling at a constant speed v. This is the speed at, or this is the velocity vector at time t naught, and this is the velocity vector at time t, some short amount of time after, and it travels some short angle theta. So if we look at the change in velocity, well, we can do that by drawing our initial velocity and our final velocity vectors with the same starting point, the tails at the same point. The change in velocity is the vector that goes from the tip of our initial velocity to the tip of our final velocity. And we get a velocity vector here, or a change in velocity vector. Notice that this forms an isosceles triangle with an angle theta. We can also think about the distance traveled by our object going in circular motion. It travels some distance, velocity times time. That's this arc here. And notice that this is also an arc of angle theta. Now, if this angle is really, really small, then this arc is really just the side of a triangle. The length of that side is equal to v times delta t. So we're actually going to have two isosceles triangles, and since they have the same angle theta, they're similar. So we can set up a ratio. Delta v over v, which is the length of this side, is equal to v delta t over r. If we solve that for delta v over delta t, we get v squared over r. Now delta v over delta t is actually the acceleration. So we end up with a magnitude for the acceleration when we're moving in circular motion. Centripetal acceleration is equal to v squared over r, and that's an important equation. Now, one other thing to note is this delta v, and therefore the acceleration, has a direction, and it points towards the center of the circle. Our centripetal acceleration is always going to go towards the center of the circle. Centripetal means center pointing. So at any given moment, our velocity is pointing tangent to the circle, and our acceleration, our centripetal acceleration, is pointing towards the center of the circle. If the object suddenly broke from circular motion, it would travel in a line tangent to the circle. That is, if we removed the force, or if we stopped the acceleration that was pulling towards the center. It would just go off in a straight line. Just like that. Okay, so let's think about this. Two identical cars are going around two corners at 30 meters per second. Each car can handle up to 1 g. The radius of the first curve is 50 meters, and the radius of the second is 100 meters. Do either of the cars make the curve? So let's find the centripetal acceleration. AC equals v squared over r. So for the first curve, it's going to be 30 meters per second squared over r, which is, the first curve is 100 meters. That'll give us the acceleration, 30 squared over 100, equals 9 meters per second squared. I'm not doing correct sig figs here. I'm not worrying about sig figs. So 1 g is equal to 9.8 meters per second squared. This is less than 1 g, so it will make the turn on the 100 meter curve. If we look at the 50 meter curve, our centripetal acceleration is again v squared over r. So that's going to be 30 meters per second all squared over 50 meters, which is 30 squared over 50, 18 meters per second squared. This is more than 9.8, so it is not going to be able to make the curve. The curve is too tight. It would have to accelerate way too much in order to make that curve at that speed. So we can ask these questions. Are force and mass a direct or inverse relation? Are force and speed a direct or inverse relation? Are force and radius a direct or inverse relation? And based on what we know about Newton's second law, force is proportional to mass, so it is a direct relation. We also know that force is proportional to acceleration. So if we think of force equals ma, force is going to be equal to m times, if we're moving in circular motion, v squared over r. So force and speed are going to be also a direct. If you're moving faster, you feel a greater force if you're going around that curve. Force and radius are an inverse relation, because if you go over a larger radius at the same speed, you feel less of a force. It's easier to go around a large curve than a tight curve. Last of all, a car will skid when the centripetal force required to make it turn is greater than the force of friction. What are two things the driver could do to lessen the change of a skid, lessen the chance, it's a typo, chance of a skid in a curve? Well, one thing they could do is they could go slower, because that's going to reduce the centripetal force. Another thing they could do is take a wider turn, because that's also going to reduce the centripetal force, or centripetal acceleration. So by Newton's second law, whenever there's acceleration, there's a net force to cause it. Centripetal force is mass times acceleration centripetal. So whenever we have, as we saw in the last slide, whenever we have centripetal acceleration, the net force is equal to mv squared over r. And that's sometimes called the centripetal force. This is an important equation, because we can then relate that to free body diagrams and solving for the net force. Centripetal force is not a new separate force in nature. It's really just the result of other forces that happen to point towards the center of a circle. If you swing something around in a string, the tension force is the centripetal force. If there's a satellite in orbit, gravity is the centripetal force. If a car is going around a curve, friction is the centripetal force that's pulling towards the center of the circle. Here's an example problem. A 1.25 kilogram toy airplane is attached to a string and swung in a circle with radius 0.50 meters. What was the centripetal force for a speed of 20 meters per second And what provides the centripetal force? So we have an object, it's being swung around in a circle of a certain radius. That radius is 0.50 meters. We need to find the centripetal force and what provides that centripetal force. Well, the only force acting on our plane in the horizontal direction is the tension. There's also going to be some mg pulling down, but our tension is the centripetal force. So let's solve for centripetal force. It's equal to mv squared over r. Plug in numbers, 1.25 kilograms times v, which is 20 meters per second, all squared, over r, 0.50 meters. We get our centripetal force equal to 1.25 times 20 squared divided by 0.5. Woo, that's a lot. 1,000 newtons. So it takes a lot of force to swing that toy airplane that fast. Keep in mind, 20 meters per second is quite fast. That's about on the order of 50 miles an hour. Oh, there's our answer. Oh, and our centripetal force is the tension in the string. So what affects our centripetal force more? A change in mass, a change in radius, or a change in speed? Think about that one for a second. It's going to be a change in speed, since from our equation, centripetal force equals mv squared over r. Velocity is squared, so a change in speed will be more of an effect than a change in mass, which is not squared, and radius, which is not squared. When a car travels around an unbanked curve, static friction provides the centripetal force in this case. So by banking a curve, we can reduce the reliance on friction for a given speed. This is what we do on racetracks and just often curves in general on highways. So here our car is going in a circle here. If we draw a free body diagram for the car, gravity points down and the normal force points perpendicular to the surface. If our car is not sliding up or down the slope, then the normal force points up, the y component of the normal force points straight up and cancels gravity. And the x component of the normal force is our centripetal force, assuming no friction. So, Fn sine of theta is equal to mv squared over r, since it is the centripetal force. The y component cancels the weight of the car, so normal force cos of theta is equal to mg. And we can combine those equations, dividing the x by the y. We get normal force sine of theta equals mv squared over r divided by normal cos of theta equals mg. From sine of theta over cos of theta equals tangent of theta, we get tangent of theta equals v squared over rg. Notice there's no mass, it cancels in this scenario. In the Daytona International Speedway, the corner is banked at 31 degrees and r is 316 meters. What is the speed that this corner was designed for? Well, we can plug into the equation. Let me write out the equation one more time. Tan theta equals v squared over rg. And if we solve for v, we're going to get v squared equals rg tan theta. And so then v equals square root of rg tan theta. So let's plug in our numbers. V equals the square root of r, which is 316 meters, times 9.81 meters per second, times tan of 31 degrees. And we plug that into a calculator, we get 43 meters per second. So that curve can handle 43 meters per second, or about 96 miles an hour, if there's no friction. But cars go a lot faster. How do they go faster without sliding off that curve? The answer is there's friction, and friction between the tires on the road provides the rest of that centripetal force. So, why do objects seem to fly away from you in circular motion when they're moving in circular motion? This is also a typo, fly away, when they're released from circular motion. What happens is they really go in a straight line according to Newton's first law, and so they are getting farther away from you. If you keep rotating, they'll look like they're in front of you, getting farther away from you. How does the spin cycle in a washing machine work? And this is what your washing machine probably uses to partially dry out your clothes. It spins really fast at the end. Well, what happens is the normal force is going to hold the clothes in place as they move in that circle. However, the water is going to continue moving in a straight line. There are holes in the side of the washing machine, or the top and bottom. And so the water can actually go through the walls, and it moves in a straight line while the clothes are held in place by that centripetal force. In summary, for uniform circular motion, we move at a constant speed in a circular path. The centripetal acceleration points towards the center of the circle, and the magnitude is v squared over r. The centripetal force is the net force during uniform circular motion. It points towards the center of a circle, and the magnitude is mv squared over r. That's all. Bye.